Hello, hello. Welcome, welcome. So today we're going to read the new Anthropics circuit thread. So this is in the earlier streams we read the original digital circuit thread. Now we're reading. This is the newer one by Anthropic. Uh, so yeah, my audio looks okay. I don't think today's stream will probably be quite a stream because it's in the early morning. So yeah, let's start. Uh, maybe. These are actually these ones. Yeah, we'll just go through these ones. These are just the ones selected here. So yeah, a mathematical framework for transformer circuits. Or maybe we'll just go through everyone, right? Um, yeah, so mathematical framework for transformer circuits. Transformers language models an emerging technology that's gaining increasing but okay. It for Anthropic. Should I have a third one? Like name it third one or not? Maybe not. Transformer language models are emerging technology that can increasingly broad real world use. For example, GPT-3. How these models scales? As these models scale, they are often indebtedness. When did this come out? December 2021. When did ChatGPT come out? November 2022. Okay, so this is before the AI hype. Uh, 10 years after language model is trained, both creator and users routinely discover model capabilities, including problematic behavior they were previously unaware of. One avenue of addressing this model is mechanistic interpretability, attempting to reverse engineer the detailed computations performed by the transformers. What is mechanistic interpretability? Field of AI research focuses on understanding how neural networks process information at a detailed mechanistic level. Instead of treating models as black boxes, this approach aims to reverse engineer all the internal structures such as neuron. Okay. Okay. Attempting to reverse using the detailed computation performed by the transformers. Similar to a program might reverse engineer complex point. Okay. This is a very it could potentially provide more very compressed. Explaining okay. This paper a previous project still thread has achieved the reverse engineering models, but so far hasn't been a comparable project for the transformers or language model. Or there hasn't been a comparable project for transformer or language models. In this paper, we attempt to take the initial, very preliminary steps towards reverse engineering transformers. Given the incredible complexity and size of modern language models, we have found it most fruitful to start with the simplest possible model and work our way up from there. Our aim is to discuss simple algorithmic patterns, motifs, or framework that can subsequently be applied to larger complex models. Specifically, the paper will study transformers with two layers or less, which have only attention blocks. This is in contrast to large modern transformers like GPT-3, which is 96 layers. Okay. This, okay, I know that. The authors are trying to replicate what the original circuit thread did for Salem, but for transformer exactly. This is where we try to okay. We find that by conceptualizing the operations of transformers in a new but mathematically equivalent way, we are able to make sense of these small models and gain significant understanding of how they operate internally. Of particular note, we find that specific attention heads that we term induction heads can explain in context learning in the small models, and that these heads only develop in model with at least two attention layers. Of particular note, we find a specific attention heads that we term induction heads that can explain in context learning in small models, and that these sets only develop in models with at least two attention layers. Hmm. We also go through some examples of these sets operating in action on specific data. We don't attempt to apply our insights to larger models in the first paper, but in a forthcoming paper, we will show that both our mathematical framework for understanding transformers and the concept of induction head continues to be partially relevant for much larger models. Okay. What is okay? Wait, what? Summary of results. Okay, we are starting with the summary of results. The conceptual takeaway. The transformer overview, model simplification, high level architecture, virtual weights and residue stream as communication channels. Attention heads are independent and additive. Attention head as an information movement. Zero layer transformers, one layer transformer, the path expansion trick. Interpretation as skip diagrams. 2K matrices. Okay, there's a channel. Hmm. Okay. We'll look into that later. Three kind of decomposition. Term importance analysis. Algorithm for measuring margin loss reduction in nth order terms. Criticism of attention as explanation. Bertology. The research on attention heads mentioned above is often grouped in a larger body of work called Bertology, which studies internal representation of transformer language model representation, especially BERT. Hmm. Mathematical framework. Since the obligation of significant follow-up has greatly clarified and extended the preliminary ideas I've attempted to explore, we briefly summarize several salient lines of research below. As of February 2023, okay. The biggest weakness in this paper has been that we have little traction on understanding MLP layers. We speculated this was due to the phenomenon of superposition. Since publication, more has been learned about the MLP layer neurons. MLP layer neurons are typically uninterpretable, provide significant evidence for typical neuron in transformer language model being polysemantic. We are led to see that we weren't the only one finding this. Hmm. Superposition, toy model superposition significantly elaborated on superposition hypothesis and that and demonstrated it on toy models. Published interim report on how one might remove features from superposition. Explore the prototype lens, polytop lens, an alternative hypothesis, or at least a perspective through superposition. What are some models trying to represent MLPs? Partition and compression diagram. Okay. Okay, summary of result. Reverse engineered result. To explore the challenges of reverse engineering transformer, we reverse engineer several toy attention only models. Just going to search and see what happens, what comes out. Attention models can be integrated into various types. I think I'm missing some context. Give me a second. Explain the inner working and understanding of the transformer architecture in detail. Make it crystal clear. Okay, transformer architecture overview. We have an encoder decoder. Each layer both has encoder. Each layer in encoder and decoder consists of multi-head attention, feed-forward neural network, normalization, reciprocal connection. Encoder breakdown. Encoder takes in input and output to contextualize the representation of each token. Wait, my bad. I want this thing here. So takes an input sequence and output. Encoder takes an input sequence and output a context or representation for each token. Okay, so as we put in each token, okay, the understanding is given to the decoder. Token embeddings, position encoding. What of the tokens are converted into embeddings for the embedding layer? Yeah, then position is added. Then comes the self-attention mechanism. The core idea is this: it's to compute the relationship between words in a sequence. Each input token is projected into three vectors: query, key, and value. Okay. The scale dot product attention mechanism is applied. QKT, query into key, computes the attention score between tokens. So when we put in a word, no, we don't put in a word, we put in a list of words. When we do that, attention score is computed between all those words. Division, softmax, normalized score. So what will we have? We'll have a layer. No. No. First, we will get the embedding for the whole tokens. No, we will take the embedding for the current word, and then we will use the other words embedding to update the current words embedding using self-attention. That's how attention works. Right? Others will contribute to update the embedding. Multi-layer attention. Instead of one attention function, multiple independent attention heads are used. Okay, this works in parallel. Feed forward neural network. Output is passed through a position-wise FNN. Decoder breakdown. It has mass self-attention head. Okay, yes, that's it. Check for the challenge of reverse engineering transformers. Here, reverse engineers several toy attention only models. In doing so, we find zero layer transformers. Model bigram statistics. The bigram table can be accessed directly from the weights. Okay. Zero layer transformers. What is that? Simpler version of transformer that has no additional traditional layers, other no multi-head attention or no feed-forward layers. Instead, it typically consists of only embedding and position encoding. No, no attention mechanism. One layer attention only transformers are ensemble of bigram and skip diagram. Two layer attention only transformers can implement more complex algorithm using superposition of attention head. These compositional algorithm can also be detected directly from the weights. The bigram and diagram table can be accessed directly from the weights without running the model. This skip diagram can be surprisingly expressive, including implementing very simple uncontext learning. Notably, two-layer models use attention head superposition to create inductive heads. One and two layer attention only transformers are very difficult algorithms to perform in context learning. On that, many subtle details of a transformer requires to approach reverse engineering each and every. For now, briefly summarize. We'll expand on the terminology as we get to the appropriate sections. And you claim the any of these points are necessary now, or many are impressive explicitly present in other papers. Attention head can be understood as independent operations, each outputting a result is added to the residual stream. Attention heads are often described. Attention heads can be understood as independent operations. Quantular transformers is very different according to performing context only. Tubular head is qualitatively more sophisticated. Hmm, okay, let's put you there. Attentions are often described in alternative concatenated and multiply formulation for computational efficiency, but this is mathematically equivalent. Attention only models can be written as a sum of interpretable end-to-end functions, mapping tokens to changes in logic. Hmm. Attention only models can be written as a sum of interpretable end-to-end functions, mapping tokens to changes in logic. Attention can be understood as having two largely independent computations. A query key circuit which computes attention patterns, an output value circuit which computes how each token affects the output pattern too. Am I understanding much now? Key query and a value vectors can be thought of as intermediate results to computation of low rank matrices. It can be useful to describe transformers without reference to them. Hmm. Key query and value vectors can be thought of as intermediate results in computation of low rank matrices. Composition of attention has greatly increased the expressivity of transformers. There's very different ways attention which can compass corresponding to keys and query composition are very different from value composition. All components of a transformer, token embedding, attention head, blah blah blah, communicate with each other by reading and writing to different subspaces of residual stream. Hmm. Rather analyze the residual stream vectors, it can be helpful to decompose residual stream into all these different communication channels corresponding to the path through the model. And these papers are very hard reads. In many cases, we have found it helpful to reframe transforms in equivalent but non-standard ways. So, mechanical interpretability requires us to break models down into human interpretable pieces. An important first step is finding the approximation which makes it easiest to reach number the models. My stream model is fine, right? Hmm. All good, sir. In modern deep learning, for good there is for good reason a lot of emphasis on computational efficiency, and our mathematical description of models often mirror decisions in how one would write efficient code to run the model. Sure, but when there are many equal ways to represent same computations, likely that the most interpretable representations and the most computationally efficient representation will be different. Obviously, reviewing transformers will also let us align on terminology, which can sometimes vary. We'll introduce some notation in the process, but since the notation are used across many sections, we'll provide detailed description in notation. This for concise reference. Now, model simplification to demonstrate the idea in this paper in its cleanest form. We focus on toy transformers with some simplifications. In most part of the paper, we will make a very substantial change. We focus on attention only transformers, which don't have MLP layers. This is for primary MLP layers are very difficult to. This is a very dramatic simplification of the transformer architecture. We are partially motivated by the fact that circuits with attention head present new challenges not faced by the discrete circuit work. The partly motivated. Okay. Considering them in isolation allows us to give an especially elegant treatment to those issues. Okay. But we also simply had much less success in understanding MLP layers so far. Normal transformers has both attention and MLP layers. There are many circuits mediated primarily by attention heads which we can study. Some of which seem important, but the MLP version have been much more harder to get traction on. The major weakness of our work that we plan to focus on in the future dispatches. We will have some discussion of transformers with MLP layers in the later sessions. We'll also make several changes that we consider to be more superficial and are mostly made for clarity and simplicity. We do not consider biases, but a model with bias can always be simulated without them by folding them into weights and creating a dimension one. That is always one. Additionally, biases and attention only. Additionally, biases in attention returns out mostly multiply out to function B bias. B biases on the logics. We also ignore layer normalization. It has a fair amount of complexity to consider explicitly. Yes, if layer down can be merged into adjacent weights. We also expect that modulo some implementation nuances. Layer normalization could be substituted for batch normalization. There are several variants of transformer language model. We focus on autoregressive decode only transformer language models such as GPT-3. Original Transformers paper had special encode decode to support translation. The authors focus on an autoregressive. Okay. Without any MLP layer and layer normalization. The transformer starts with token embeddings followed by a series of residual blocks. Hmm. Residual blocks in transformer help refer to a skip connection added around the key components like attention and feed forward layers. Okay. They do use stabilize and improve linear flow. A transformer starts with token embedding, followed by a series of residual blocks, and finally a token unembedding. Each residual block consists of an attention layer followed by an MLP layer. Each residual block, okay, mm, maybe it refers to this thing. Multi attention layer followed by a feed forward layer. Okay. Both both the attention and MLP layers read their input from the residual stream by performing linear projection, and then write all the result on the residual stream by adding a linear projection backend. Each attention layer consists of multiple heads which operate in parallel. Hmm. Token embedding. And this is the mainstream, I guess. Each attention head is run and added to the residual stream. Okay. An MLP layer is run and added to a residual stream. and both of this constitute one residual block. Virtual is a residual stream as a communication channel. One of the main features of the high-level architecture of transformers is that the layer at each layer which result to what we call residual stream. The residual stream is simply sum of the output of all the previous layer and the original embodiments. We generally think of the residual stream as the communication channel since it doesn't do any processing itself and all that communicates to it. Hmm. Okay. Hmm? What happened? What happened? Like what happened? I have no idea. Okay, anyways, this number you. The residual stream has deeply linear structure. Every layer performs an arbitrary linear transformation to read in the information from the residual stream at the start and perform another arbitrary linear transformation before adding to write. The residual stream has a deeply linear structure. Every layer performs an arbitrary linear transformation to read in information from the residual stream at the start, and this ignores layer normalization at the start of each layer, but up to a constant scalar, the layer normalization is constant affine transformation and can be folded into linear transformation. Blah, I don't know. This linear additive structure of the residual stream has other important applications. One major consequence is that the residual stream doesn't have a privileged basis. We could rotate it by rotating all the matrices interacting with it without changing model behavior. An especially useful consequence of the residual stream being linear is that one can think of implicit virtual weights directly connecting any pair of layers, even though supported by many other layers, multiplying the interaction through the residual stream. These virtual weights are the product of the output weights of one layer with the input weights. The residual stream is modified by a sequence of MLP and attention head, reading from and writing to it in linear operation. Hmm. Because these operations are linear, we can multiply through the residual stream. Each layer writes a residual stream by adding a linear project. Okay. Multiplying all the weights reveals virtual weights, implicitly connecting to each pair of layers. By using different subspaces of the residual stream, a layer can send different information to different layers or even not interact with the residual stream is a high dimensional vector space. Okay. So one thing I got from this thing is we can think of transformers as a residual stream in which layers take in linear projection from the residual stream, does operations like self attention, etc., and then writes back to the residual stream after a linear projection again. Okay. How do you vector space? It means that layers can send different information to different layers by this is especially important to get our attention head since every individual head operates on comparatively small spaces and can easily write to completely disjoint subspaces that do not interact. Okay. The residual stream can be very high dimensional, hundreds to ten thousands of dimensions. Oh man, of dimensions. So each layer can add and write to the residual stream in a way that doesn't interact with other layers. That's cool. Once added, the information persists in subspace unless another layer actively deletes it. From this perspective, dimensions of residual stream become something like memory or bandwidth. The original token embeddings as well as the unembeddings mostly interact with relatively small fraction of the dimension. This leaves most dimension free for other layers to store information in. I think that we should explore residual stream bandwidth to be in very high demand. Generally far more computational dimensions such as neurons and attention head. Neurons and attention head result dimension. There are generally far more computational dimensions than the residual stream has dimensions for to move information. Mm. Because a single MLP typically has 4 times number of neurons and the residual stream dimensions. So, for example, a layer 25 of a 50 layer transformer, the residual stream has 100 times more neurons as it has dimensions before it. Try to communicate with 100 times as many neurons as it has dimensions after it somehow communicating in supervision. Doing patterns are like the bottleneck at question and we expect them to usually be challenging to interrupt. This is the major reason why we will try to pull apart the different streams of communication happening to the residual stream apart in terms of virtual weights rather than studying it directly. Or because of the high demand of residual stream bandwidth, we've seen hints that some MLP neurons or attention head may perform kind of memory management role, clearing residual stream dimensions set by another layer by reading information and writing out the negative version. Attention heads has information movement. Attention heads are independent additive. As we seen above, we think of transformer attention layers as several completely independent attention heads, which operate completely in parallel and each channel their output back to the residual stream. But it isn't how transformer layers are typically present and may not be obvious the equivalent. The original Vishwani paper, the output of attention layer is described by Sam. The incarnation evaluation is often preferred because it provides larger more attention handles information movement. But if attention acts independently, what do they do? They kind of ask different question and get a different answer, right? That's the general knowledge. The fundamental action of attention head is moving information. What? Moving information? I mean, uh, they read information from the residual stream of one token and write to the residual stream of another token. Okay, that's true. Okay, so that's just moving information, huh? Okay. The main observation you should take away from this session is that which token to move information from is completely separable from what information is read to moved in and how it is returned to the destination. Mm. Helpful to write attention in non-standard way. Each of these steps can be written as a matrix multiplication. Why don't we collapse them into single step? If you think project result vectors out of each token, mix the okay. Noting that the formation is mathematical, actually implementing attention this way would be horribly inefficient. Okay, I don't know why I'm able to like copy multiple things like this, but okay, it's gone. Observation about attention head. A major benefit of rewriting attention head in this form is the serves a lot of structure it may have been previously hard to observe. Attention head have more information about okay. Attention head is really applying to linear operation, which operates on different dimensions and act independently. A governs the token information is moved in from mod to okay. Man, I'm not understanding much. I think I'm going to stop it right now. WK and WK always operates together. They're never independent. Wow, I know that. Products of attention head behave much like attention head themselves, with a distributive property. The result of the product can be fundamental, can be seen as functionally equivalent to attention head, with an attention pattern which is the composition of two heads and an output value matrix. And I'm not understanding much. I'm going to stop here. Thank you for watching. Goodbye.